Hey everybody, what's going on? This is Mr. Kozad back again with another lesson for you on 10.2. This is Arithmetic Sequences and Series. The purpose of this lesson is to catch up those of you that missed this lesson for some reason, or maybe your teacher was gone. This is kind of to help you be ready for your quiz next time. Okay, so if you do not have a copy of the 10.2 notes, I would stop now. Pause the video, go to It's Learning, and print a copy of the 10.2 slides so that you can take notes as we go along through this. It's going to be pretty quick for you. And what I'm going to actually do here is I've got my notes made already, and I'm going to kind of notate those for you and kind of narrate them, give you some ideas of what we did, why we did it. Okay, so here we go. Let's jump right into 10.2, Arithmetic Sequence and Series. Now the first thing that you want to see here is you want to see that an arithmetic sequence, what in the world is that? Okay, to be arithmetic, you've got a sequence that has a common difference that's either adding or subtracting the same number each time. Okay, it has to be adding or subtracting to be arithmetic. If you're multiplying or dividing, that could potentially be a sequence, but it's not going to be arithmetic. Okay, so the specific case to be arithmetic is it has to be a sum or a difference, okay, addition or subtraction. So this problem asks you to determine the common difference and the next four terms of the arithmetic sequence. So as we look through this, we see negative 53, negative 36, negative 19. And as you do a little bit of number crunching, you can see that the difference here is plus 17 every single time. So the common difference here is plus 17, and this makes it arithmetic because it's plus 17, not times 17, not divided by 17, but it's plus. Okay, to be arithmetic, remember, it has to be either plus or minus the same number. So if we continue this pattern, we very clearly get negative 2, negative 19, plus 17 is negative 2, plus 17 gets me to 15, plus 17 gets me to 32, plus 17 gets me to 49. Okay, the next thing you're gonna have to know for this lesson is how to write the equation of a sequence in both explicit and recursive forms. Okay, this might be beneficial for you, but the form that I'm going to use the most is an equals dn plus c, where d is the common difference and c is going to act like the y-intercept. Okay. So this direction here is find both an explicit formula and a recursive formula for the nth term of the arithmetic sequence. Okay, so here's my sequence, 14, 3, negative 8. First thing to do is to find the common difference, that's minus 11. So we take the previous term minus 11. So my common difference, d, equals negative 11. Now what I did is I actually started with the recursive formula, okay, because recursive is pretty easy here. Your current value, or an is going to equal a of n minus 1, which again is just a fancy way of saying the previous term minus 11. So instead of saying a n minus 1, what if I said the previous term minus 11? That makes a lot more sense. But to use the correct notation, you're going to do a of n minus 1. That's how we represent the previous term. So our first term is 14, so a1 is 14, and this is only useful for n values that are greater than or equal to 2. So that's how we do recursive. Now explicit, we're going to have to use this formula that we have, an equals dn plus c. We've already figured out that d is negative 11, so I have an equals negative 11n plus c. Now what I do to solve for c is I know the first term, when n equals 1, I know the term is 14. So I plug a 14 in for an and a 1 in for n and solve for c. When I do that, I get c equals 25. So there, if I build my formula, I get an equals negative 11n plus 25. All right, so let's keep moving. Okay, here's the next way that you could be asked a question in 10.2. Okay, it says find the 41st term of the arithmetic sequence, 11, 4, negative 3, negative 10, and so on. Okay, this pattern would continue forever. So the first thing you want to identify, obviously, is the common difference. And it doesn't take you long to identify the common difference as minus 7. So if I take my form an equals dn plus c, I'm going to plug negative 7 in for d, and I'm going to use the first term is equal to 11. So I plug 1 in for n and 11 in for an, and I get c equals 18. Then I put it all together, an equals negative 7n plus 18. So a of 41 is just going to equal negative 7 times 41 plus 18. I get negative 269. Now that is a much faster, more efficient way to do this The other alternative is you could literally write out this sequence 41 times and you would still get to negative 269. That doesn't sound very pleasant to me, nor should it to you. So it would be really advantageous for you to know how to write an explicit formula and use that to find the 41st term. Okay? Okay, so this is worded a little bit differently, but same kind of concept. It says find the first term of the arithmetic sequence for which A44 equals 229. So that means the 44th term in the sequence would be 229. And D, our common difference, is 8. So if I build that formula, I know that A of 44 is 229. So I've got 229 equals 8, the common difference, times the n value, which in this case is 44. And I don't know C plus C. But you can solve for C pretty easily to get negative 123. So then if we put that all together, we get AN equals 8n minus 123. And if I'm asked for the first term, I plug a 1 in for n, and I get 8 times 1 minus 123 gets me to negative 115. Okay, this problem is a little bit different, but this is the next kind of thing you're going to be asked about in this section. It says write an arithmetic sequence that has 5 arithmetic means between 6.2 and negative 1.6. Okay, so this problem is going to be really tricky for you if you don't know what they mean by arithmetic means. All that really means is that there's going to be 5 numbers that are equally spaced between 6.2 and negative 1.6. So the way that I illustrated that is I started with 6.2 and I ended with negative 1.6. And I put 5 lines in between here to represent the 5 different numbers that are going to exist in the sequence between 6.2 and negative 1.6. Again, why is it 5? Because that's how the problem was defined. If this were 4, there'd be 4 numbers. If it was 10, there'd be 10 numbers in between. Whatever this number is how many numbers are in between the two numbers that are given, 6.2 and negative 1.6. So the way that I figured out the common difference here is I figured out how far apart 6.2 and negative 1.6 are. I did that by subtracting. When I do 6.2 minus negative 1.6, I get 7.8. Okay, so then I do 7.8 divided by 6 to get 1.3. Now, if you're like me or a lot of the students in class that were here for this lesson, you might be curious, why aren't we dividing by 5 since there's 5 arithmetic means? Well, the way to illustrate that is you actually draw an arrow applying the common difference from 6.2 to 4.9 and so on, and we get 1, 2, 3, 4, 5, 6. So we're applying that common difference 6 times. So we're going to take our distance between those two numbers and divide that by 6 to get 1.3. So then you simply take the 6.2 and subtract 1.3 to get 4.9, subtract 1.3 again and again and again to find the 5 numbers that exist between 6.2 and negative 1.6. Here's another chance for you to practice. Obviously the answer choice is C. I'd pause the video here and make sure that you can do this and do it correctly and get C on your own. If you're not getting C on your own, just make for certain that you're subtracting correctly. The distance between 16.2 and 14.7 is 1.5. Again, this has 5 arithmetic means, which means 5 numbers in between, just like the last one. So I'm going to divide by 6 here to get 0.25, and then subtract that to get the missing terms in between 16.2 and 14.7. Okay, here's the next challenge for us, is to figure out a quadratic model for this sequence. Okay, now here's the sequence that you see here, 0, 5, 12, 21, 32, 45, and so on. Okay, and what we can actually do here is we have find our difference. We get 5, 7, 9, 11, 13, and so on. Clearly that's not arithmetic. Okay, but what we can actually look at is you can look at what's called the second difference. Look at the difference of the difference. And we see that the difference of the difference is plus 2, plus 2, plus 2, plus 2. If the second difference is the same, we can deduce that that sequence is a quadratic sequence. Okay? So ideally I'd pull up my graphing calculator and show you what to do next, but I don't actually have my graphing calculator available. But what we're going to do here is we're going to do a quadratic regression on the calculator to figure out what the formula is. Okay, so the formula we're looking for is an squared plus bn plus c. And what you're going to do is you're going to plug these 3 values in. Oh, time for B-lunch. You're going to plug these 3 values in, okay, to your calculator, and you're going to do what's called a quadratic regression. If you don't know how to do a quadratic regression on your own, you can Google it, honestly, and find probably several videos and sources to show you how to do that. Okay, so again, I would ideally pull up my calculator and show you how to do that. But if you don't know how to do that, stop now and go try to find a resource to help you with a quadratic regression. If you can't find one or want one-on-one instruction, come in and see me or one of your other teachers, and we'd be more than happy to show you how to do that. Okay. Here's just another opportunity for you to practice a quadratic model if you choose. You could pause the video now and try it on your own again, seeing if you can get the quadratic model for that. You should get answer choice B. Okay, this is approaching one of the last things you have to do here. Okay, so we're going to talk about how to find the sum of a finite arithmetic series. So this is a new formula that we can use here. If you printed the notes yourself, you can cross off that second one. We won't use that. We'll only use this first one here. And this is Sn equals n over 2 times a1 plus an. And remember that this notation here is talking about a series, so it's asking for the sum of all the terms up to n of a sequence. Okay? So let's see how we can use this in action. Okay, so it says find the sum of -3, 2, 7, 12 plus some number of terms in between all the way up to 157. Now we obviously know that -3 is the first term. We know that 2 is the second term, 7 is the third term, 12 is the fourth term, but we have no idea which term is 157. So what we're going to have to do is we're going to have to write an explicit formula for the sequence. The common difference here is 5 plus 5. So as I'm building my formula, I have 5n plus c. Again, I'm going to take that first term, -3, plug that in here, and make n equal to 1, because that's the first term in the sequence. Simplify that for c, I get c is -8. So my explicit formula is 5n minus 8. Well, then what I can do is I know that 157 is going to be the nth term of the sequence. So I plug 157 in for an, but I don't know what n is. I'm going to solve for that. So if I solve for n, I get n is 33. So that tells me that 157 is the 33rd term in the sequence. So I'm going to find the sum of the first 33 terms of this sequence. So S33 equals 33 over 2 times A1 is -3 and A33 is 157. Plug and chug that in a calculator or mentally, or you can do it with scratch paper, and you should get 2541. Here's two more kind of applications of that same concept. Okay, it says find the 17th partial sum of the arithmetic series. So what we're going to do here is we're going to find the 17th, the sum of the first 17 terms of the series. So if you want to do it the hard way, you can continue this series 17 times and then add up all those numbers, or you can use that nifty little formula we just had. Okay, so S of 17 equals 17 over 2 times A1, which is 53, plus A of 17. Now, unless you write it out 17 times, you aren't going to be able to know what A of 17 is. So what I actually did is I used our explicit formula to find A of 17. So I started with the common difference. I got the common difference to be -22. So, excuse me, I know my common difference is -22, and I know the first term is 53, so 53 goes here. I replace n with 1, and I solve for c to get 75. Plug that all together, or put that all together, and plug 17 in for n, and I get -299, which is my A17 value. Plug this expression in, press enter, you get -2091. Now this notation is a little bit different. Okay, this is sigma notation, same kind of concept, but just sigma notation. So we're going to take n plus 6 and we're going to add all those terms starting at n equals 10 all the way up to n equals 32. Now you could do that 23 times and add up those numbers, but I don't think that's very efficient. Okay, let's use our nifty little formula here. So we have S of 23. Now let's pause for just a minute and talk about where that comes from. Okay, you're not starting at 1 and going to 32. So this is not going to be 32. You're actually starting at 10 and going to 32. Now somebody might be saying, well, isn't 32 minus 10 22? So shouldn't that be 22? Well, that's actually 23 terms because you have to count both the 10 and the 32. They both count as terms. So it's 23 terms. Okay, so we plug 23 in for n, so 23 over 2. A of 10, that's another thing that you might have made a mistake on. We're not talking about A1, we're talking about A10 because that's where we're starting. So A10, I literally plug 10 in for n. 10 plus 6 gives me 16. A of 32 is where I'm ending, so I plug 32 in for n, and I add 6 to get 38. So here we go here. We just plug and chug that in our calculator or by hand or mentally, and you get 621. So our last item here is a word problem, which I'll give you some time to read on your own and kind of work through. We're going to use that formula that we had previously. What you're going to see here is that the increments here are by 10,000 CDs, so every term in the sequence is equal to 10,000 CDs. So if you're trying to get up to 500,000 CDs, you don't have to go to A 500,000, you only have to go to A 50, because remember, each increment counts as 10,000 CDs. So they give you the first three terms in the sequence, and you can clearly see that the difference is $2,500. So every 10,000 CDs you add is an additional $2,500. So I'm going to find the explicit formula for the sequence. Common difference, 2,500. I plug in the first term of the sequence, n is 1, 10,000 is A1. I find my C value. I put that all together, and then what we do is we use this formula to spit out our A50 value. We don't know what number this is without repeating the cycle 50 times, but I plug in 50 for n and I get 132,500. So that's my A50 value. So now what you have to do is you have to take the sum of the first 50 terms of the sequence, S50. So we have 50 over 2, 10,000 is A1, 132,500 is A50. Plug all that in, press enter on your calculator, and you get 3,562,500. I know that was super quick. Some of it may have felt rushed. Please feel free to rewatch any of it that you need to, and don't hesitate to ask your teacher if you have any specific questions. I hope that was helpful. We'll see you next time.